Record. Okay, hello everyone and welcome to the SLDS monthly webinar. My name is Jamie Spicer. I'm an assistant professor at Wake Forest School of Medicine and I'm organizing this webinar series that is sponsored by the section on statistical learning and data science of the American Statistical Association. Today we are honored to have Dr. Jean Feng talk about deep learning. Dr. Feng is an assistant professor in the Department of Epidemiology and Biostatistics at the University of California, San Francisco. Her research interests are on the interpretability, reliability, and regulation of machine learning algorithms for healthcare. Dr. Feng's talk will be about an hour. Please hold your questions for the end of the talk. We will have about 30 minutes of discussion, but feel free to write in your questions during the presentation in the chat, and we'll get them lined up for afterward. The webinar is being recorded and will be available on the section website after the presentation. Again, I'd like to thank our speaker, Dr. Feng, and the sponsor of this webinar, the Statistical Learning and Data Science section of the American Statistical Association. Dr. Feng, I will turn it over to you.
Thanks, Jamie. Thanks for inviting me to give this talk. Yeah, so I'm Jean. I'm an assistant professor at UCSF. Jamie invited me to give a talk on deep learning, so I'm going to talk specifically about variable selection and architecture search, mostly in the context of dense neural networks for tabular data, and we'll get to why. And before I jump into all of that, I wanted to give a brief review of neural networks. So for those of you who are less familiar with this methodology, hopefully I can get you a bit up to speed, at least on the basics. And for those of you who know what's going on, just bear with me for a little bit. Okay, so what is deep learning? There's a lot of definitions out there. Since we're doing a statistics webinar, I'm going to try my best at defining it in more statistical terminology. And I would say that deep learning is a non-parametric machine learning method that builds large computational graphs. These are called neural networks to model complex nonlinearities, interactions, and hierarchies in the data. So on the left here, we have these nodes represent input variables. So here's a picture of my dog, and every pixel here could correspond to a node that's going into this graph. And then these intermediate nodes take in the values from its input nodes, and then it mishmashes it in some mathematical transformation, and this information is propagated through the model to produce some sort of output. And in this case, this neural network says problem child, in which case it is extremely smart. Yeah, so it's also a non-parametric machine learning method, meaning that as I get more data, I would be able to expand the size of my neural network to learn more and more flexible models. So here are just kind of some strengths of deep learning and how it might differ from some other machine learning methods. There's the universal approximation theorem that is basically why it's non-parametric. It says as you can create a sufficiently large neural network to approximate any continuous function. It's memory efficient, meaning that you don't need a lot of parameters in a neural network to start expressing very complex ideas. So if you wanted to fit a linear model with interactions, we're talking about maybe p-squared terms or whatever multi-way interaction you're trying to fit. Whereas in a neural network, the number of terms can be linear in the number of variables, even if you want to fit multi-way interactions. There's representation learning, which is kind of a big deal in neural networks, which is that as I go along the depth of the neural network, I can express increasingly abstract ideas or representations. So here's just an example from 2017 where they were looking at the innards of this neural network and found that early layers are detecting very simple diamond patterns per se. And as you keep going, it gets more and more complex. Like at the end, it's detecting these like wheel-like objects. And then neural networks are highly modular, which makes them easy to play around with and adapt to whatever problem domain you're interested in. So it's easy to add nodes, layers, modules. And this flexibility is nice. Like I'll use it as well to think about how we might do variable selection. Variable selection or architecture search. Yeah, and then there's the other obviously added bonus, which is that there's a lot of software around neural networks. So adding nodes and layers or whatever is super easy. Okay, so neural networks span a very wide range of models. They go all the way from just simple linear regression to nonlinear models with complex interactions. And to actually find the right neural network architecture, you really do have to think about this bias variance trade-off. So what I'm going to do is just really go from the simplest neural networks and build up from there, and then we'll get to actual neural networks, or I guess things that are uniquely neural networks. So there's linear regression as a neural network. So you have 4 input nodes, x1 through x4, multiplied by these coefficients w1 through w4, add on an intercept term, and then you get your output. So usually we call the weights, the coefficients weights and the intercept bias in the deep learning literature. There's logistic regression, where the only thing we've changed is adding on this the sigmoid function at the very end. And more generally, we refer to these nonlinear functions as activation functions. There's a linear neural network where we've added nodes, a layer of nodes in the middle. And it's just a sequence of linear transformations to get, so one linear transformation with these, with a matrix W1 plus this vector B1 gets you these intermediate nodes, and then you do another linear transformation. And this kind of looks like PCR, like a principal component regression. These could represent like your PCs. And then we get to a dense neural network where we've applied a nonlinear activation function in the middle. So sigma 1 here could be a sigmoid, but it could also be a hypertangent function. It could be a ReLU, rectified linear unit. Yeah, and then you can do that. You apply some other linear transformation and maybe apply another nonlinear activation function. So once you start adding multiple layers, we refer to this as a deep neural network. Of course, you can also have a wide neural network, meaning you can have many nodes per layer. Okay, so I talked about the architecture. How do you actually go about training a neural network? So if you had a specific architecture in mind, usually we apply some sort of optimization procedure to estimate the actual neural network parameters. So usually we try to minimize some sort of objective function. Here I'm just using the MSE as an example. And sometimes we tack on some sort of penalty. Very common to use the ridge penalty on the network weights. But the trained model is going to be specific to the architecture you tried out and the penalty parameter you selected. And those hyperparameters might not be optimal. So it's very important to actually employ some sort of outer optimization procedure where we test out all these different configurations for the model, the network architecture, as well as maybe other things that you think about, like penalty parameters. So you do some sort of training validation split or cross validation for this. And so there's a bunch of hyperparameters you need to think about when we are tuning that architecture. There's the number of layers, there's the number of hidden nodes per layer, and typically the number of hidden nodes per layer is different, which increases the number of hyperparameters to think about, and also maybe even which variables to include. Okay, so this is kind of the real source of pain in neural networks because there's just so many hyperparameters to think about. And so a lot of work has been done in hyperparameter optimization. There's like the simplest approach that we often use when there are not that many hyperparameters to think about, like lasso or elastic net. With only one or two or maybe three hyperparameters, it seems quite reasonable to use something like grid search. So you just test out basically you make a grid of possible hyperparameter values and then you test them. A slightly better approach when you start having a lot of hyperparameters is to do a random search. So if you know what range your hyperparameters are going to span, one thing you could do is just randomly sample in that space. And this can actually have benefits over grid search, because if some of the hyperparameters are not very important to tune, whereas some are, the random search will test out more configurations of the hyperparameters, of the important hyperparameters. And then, so these two methods are a bit more like brute force in nature. We can actually really apply like optimization procedures to hyperparameter search or hyperparameter tuning. So you can use gradient-free optimization. So something like a traditional simplex method, though right now what's very popular in deep learning is using something like Bayesian optimization, where you test out hyperparameter values iteratively, and that will help you approximate the surface of this validation loss, and hopefully you can use that to tune these hyperparameters. And then there's gradient-based optimization, where we actually take the derivative of the validation loss with respect to the hyperparameters and use that to kind of traverse the surface. Usually that's even more computationally intensive than the gradient-free one, or at least the math behind it is more complex. So there's some sort of trade-off between these two. Anyhow, so while these methods could be used to try to tune the hyperparameters, they are all pretty computationally expensive. And if we're thinking about, like, I don't know, fitting models for object recognition, and you have Google amounts of data, then yes, you probably want to spend that time doing hyperparameter optimization. But if you have a, say, more ordinary data set, you really have to think about what is the performance gain I will get from using a neural network over some other machine learning algorithm I could have used, and the computation time for actually like tuning that neural network. And sometimes the trade-off's not very clear. And so here's an example of a paper that was published a while back, where they were evaluating hundreds of different machine learning classifiers on the UCI data repository. And what they found is random forests work very well most of the time, whereas neural networks rank lower in terms of performance. And the UCI data set, the UCI data repository certainly represents kind of a biased view of what real world data sets would look like, but these numbers look a bit more reasonable to something you might see in your day-to-day work, right? Like maybe you have a decent number of observations and you have a decent number of variables. Maybe sometimes it's very high dimensional where you have a lot more variables than the number of observations, but it's not huge amounts of data. And the conclusion seems to be that if you want to analyze this type of data, an off-the-shelf method like random forest seems to work quite well, whereas neural networks don't seem to give us much more gain over them. And for this reason, neural networks just aren't like the preferred thing for analyzing tabular data right now. The other issue is that neural networks not only don't outperform other methods on tabular data, they tend to do very poorly in high dimensional settings. So kind of the question that I'm interested in that we'll be talking about for the rest of this time is there is there really no way we can construct some simple procedure for fitting a neural network that works well for tabular or high dimensional data? And to actually try to answer this question, there's a couple of pieces here. There's the first piece, which is we need to solve the problem of getting neural networks to perform at least decently on high dimensional data sets. And then the second part will be, how do you make it computationally easy, where you don't have to spend so much time on hyperparameter optimization? Okay, so that's the brief review, and hopefully now we can get started with the rest. So we're going to try to tackle those two questions. The first is neural networks in high dimensional settings. How are we going to do this? Well, we're going to try to do some variable selection here. And then the second question was, how do I do this computationally efficiently without spending too much time in hyperparameter tuning, spent on hyperparameter tuning? And what we'll try to think about is, how do we do this? How do we do variable selection and architecture selection efficiently? Okay, so let's start with the first one. So the general problem is non-parametric learning in high dimensions, which we know is a pretty difficult problem. When you don't have that much data, it's just hard to learn all these non-linearities and interactions. But still, in certain data settings, that might be really important. Like we know genes interact, and that might lead to particular patient outcomes, and maybe modeling those interactions is important. So again, we're in the high dimensional setting where the number of variables P is large compared to the number of observations N. We don't want to really make strong assumptions on the structure of the model. And the one thing that's going to hopefully make this problem tractable is that we have prior knowledge that only a subset of variables are important. So we have this sparsity. So before we solve the non-parametric problem, maybe let's dial it back and think about a simple linear model. In the linear setting, well, we would probably reach for something like the lasso, right? So rather than fitting ordinary least squares, we would minimize the MSE plus a lasso penalty. So the L1 penalty on the coefficients of the model. And this is going to encourage coefficients to equal 0. And if we have some prior knowledge about which variables form semantically meaningful groups, we could use something like the group lasso. So the only thing we've changed is adding on the summation here of L2 norms. So the L2 norm of the coefficients in each group. And this will encourage the entire group, the coefficients in that group, to be set to 0. So together, the lasso plus the group lasso penalties is called the sparse group lasso. And then if we want to relax this linearity assumption, we could fit an additive model, so the sum of smooth univariate functions. And we can try to fit, and we can do something also along the lines of penalization, so like a sparse additive model, so that our learned model will only depend on a subset of the variables. And to do that, we can add this L2 norm of the univariate functions. And this can be thought of as a functional version of the group lasso. Okay, so now let's actually, we want to go one step further, which is the additive model doesn't allow for interactions, but can we actually learn that as well? And if there are multi-way interactions, it seems like neural networks could be a reasonable approach. Like it's not very hard to start modeling multi-way interactions using a neural network, because you don't need that many parameters for that. Once you have these non-linearities and these hidden nodes, we're starting to model these interactions. But we want to have that sparsity because presumably that will help our model perform better. So how do you train a neural network? to depend on a small number of variables? Well, we know that if you set weights in the neural network to 0, then the neural network might not depend on certain variables, right? So like these 3 edges here are connected to x1, but if I set all of their weights to 0, then the neural network will not depend on x1. And we can also think about kind of more limited dependence on x1, where we set a subset of its weights to 0. Okay, so then it seems like what we can do basically is try to use this lasso or group lasso penalty to kind of do this. So this is one way to train a neural network to depend on a small number of variables, and we call this sparse input neural networks. And what we do here is to introduce a lasso penalty on the weights in the first layer. So just a general lasso penalty on all the weights here. We also introduced a group lasso penalty where the groups here are all the weights connected to the same input node. So these 3 connect to x1, these 3 connect to x2. So those are our groups, and we'll introduce group lasso penalties for each of those to encourage the entire group of weights to be set to 0. And hopefully this will help us drop entire variables from the model. And then we'll also include a general ridge penalty to encourage weights to be small. So this is mostly applied to the upper layer weights. Okay. So training a sparse input neural network is not that hard. What usually we apply something like gradient descent or stochastic gradient descent. Rather than using that, we want to introduce sparsity, so we can use generalized gradient descent instead. So at each iteration, we take a gradient step with respect to the smooth terms in the objective. So that's the empirical risk plus the ridge penalty. And then we have a second step that does a shrink and threshold operation on the parameters penalized by the sparse group lasso. And that's super simple to run, so it doesn't add much computation time whatsoever. But this is where you're going to introduce that sparsity into the neural network. And then there were 3 penalty parameters in that objective function. So we would have to tune that. And one way to speed it up a bit is to consider warm starts to accelerate training. And then there's been more recent works that explore like how can we train sparse input neural networks faster. So you can go to these papers where they basically look at something like the lasso path, which is pretty cool. Okay, let's look at how a sparse input neural network performs. So here's just a simple simulation study. We have 1,000 variables. The conditional mean is a very complex, strange function of the first 6, so x1 through x6. And we're going to fit sparse input neural network, a ridge penalized neural network, so that's just your ordinary approach to fit in a neural network, sparse additive models, and then we have 3 oracle models here just for reference. These oracle models all know which variables are actually relevant. So this is a neural network trained on only x1 through x6, or an additive model for those covariates, or a smoothing spline. Okay, so what do the results look like? So here we've varied the number of training observations, and we're looking at the MSE on the test data. The dashed lines here correspond to the oracle model. And what we see right off the bat is that ridge penalized neural networks are very bad. It doesn't do well with not a lot of samples, and it's not really doing well even with a lot of samples. So that does confirm this general idea that neural networks, a general neural network isn't going to do well in high dimensional settings. You can do better by considering an additive model, a sparse additive model. So it does much better with a small number of samples, and it'll continue to improve, though it stops improving around like 2,000 observations, which is not super surprising because it's made this assumption that the variables don't interact. So at some point, it just kind of taps out. And the interesting part is that the sparse input neural networks are doing very similarly to the additive model up to 2,000 observations, but then it continues to improve. So the model is starting to realize there's enough data to perhaps model interactions, and that's kind of where our improvement is coming from. And then here on the right, we can also look at whether or not the sparse input neural network is picking up on the correct variables. And the average magnitude of the weights assigned to the irrelevant variables is much smaller than that assigned to the relevant ones. So it does seem like the neural network can do some sort of variable selection. Okay, and then here's just an application on real world data. We're trying to predict riboflavin production from gene expression data. We have 4,000 genes, and then we have 71 observations. And we kind of see the same patterns again, basically. Like ridge penalized neural networks are very poor, perform very poorly. You can do better with sparse additive models or a linear model with the lasso. And then you can continue, and the sparse input neural network does a bit better. It doesn't do a lot better, but it does do a bit better. And you can see, well, obviously the ridge penalized neural network isn't going to do any variable selection, and the other ones do some. Okay, so the general takeaway is, well, if we introduce a lasso and a group lasso penalty, we can train neural networks that depend on a small number of variables. This improves performance, and it seems to do some sort of variable selection that might actually help us recover the true variables that are relevant. And yeah, so we do significantly better than if you didn't have the lasso penalty. And then kind of one issue that still remains, however, is that the performance of sparse input neural networks really depend on doing a good architecture search. And that's still computationally expensive. So was that small performance gain we saw for like the riboflavin production really actually worth it at the end of the day? And I don't know, even though I wrote this paper, I'm like, the performance gains are not significant enough yet to justify the hyperparameter optimization, the time spent on hyperparameter optimization, which is why we are interested in building on that approach and seeing if we can do better. So the next part is thinking about, can we do variable selection and architecture selection? Okay, so sparse input neural networks can be kind of viewed as doing some sort of kind of shifting some of the burden of variable selection from the outer optimization problem to the inner one. Like if we thought of it as like one of the hyperparameters was to select which variables to include, adding that lasso and group lasso penalty helped us perform variable selection with the trait where it does the variable selection, but we've added a few more penalty parameters. We've added, I guess, 3 penalty parameters to the outer loop. But the trade-off was worth it, right? Like specifying which variables to include, that's going to add way too many candidate hyperparameters to actually search over. But this general idea of kind of shifting that burden from the outer optimization procedure to the inner one seems to be interesting, because the question then is, can we also shift more things in, right? Like can I shift more of this burden of this architecture search into the inner optimization procedure? Can I tune the number, instead of tuning the number of layers and tuning the number of hidden nodes, can I let that inner optimization do that for me? And so we would like an inner optimization procedure that does pruning and training. And we want to make that outer optimization procedure as simple as possible. Like, can we do it with only 2 hyperparameters? Because, well, I guess a lot of common off-the-shelf machine learning algorithms don't really have a lot of hyperparameters. Typically 2 or 3 is the most we want to think about. So let's see if we can actually define 2 hyperparameters that characterize kind of the high-level characteristics of a network structure without actually specifying the specific structure. And ideally, we want these hyperparameters to kind of correspond to major axes of variation in the generalization error. And so hopefully that will make this hyperparameter search as efficient as possible. Yes. Okay. So our latest work is kind of trying to answer this question. We spend a while scratching our heads trying to figure out how you can do this with only 2 penalty parameters. Here's one proposal. So we've indeed have only 2 penalty parameters. And what we're relying on are 2 lasso penalties. So the idea is, let's try to initialize the neural network structure to be something pretty large, larger than is necessary for the problem, but we'll prune down from there. Like in this paper, the network architecture for all of the examples was 5 hidden layers and 100 hidden nodes per layer. And so this first lasso penalty is supposed to correspond to the sparsity, or it's helping us control the number of input variables to the model. And then the second lasso penalty helps us control the size of the neural network. So those are kind of the 2 major axes we're kind of targeting. And the reason we targeted that is kind of based off of some analyses we did in the previous paper, where we found those seem to be the major contributing factors to the generalization error. Okay, so we also did some tweaking to the neural network architecture. As you can see, we've added some funky edges and this input filter layer as well. So these are called skip connections that connect the output to intermediate layers. And it's pretty common in like structures like ResNet in the deep learning literature. Okay, so what is the model? How is the model defined exactly? What are these extra blue nodes? So each of these blue nodes is connected to each layer. So C1 is a linear combination of the input nodes. C2 is a linear combination of the first hidden layer, so on and so forth. And then each of these are connected to the output. So the output is a weighted combination of these blue nodes. So that's how it's defined up here. Right, so, and then each of these skip connections is associated with a parameter alpha that's going to control the weights. Okay, so why was that helpful? Well, if we look at this second lasso penalty that was supposed to help us control the size of the network, the lasso penalty is trying to help us set weights to 0. And so it could potentially set all the weights to exactly 0 and in a particular layer, and thereby removing an entire layer. It could also help us remove some hidden nodes. Remove a subset of hidden nodes in a single layer. But because we have these skip connections, it's not like we've completely broken the flow of information in the neural network. What we have now is just a neural network with 1 fewer hidden layers. So this is why we kind of refer to it as a hierarchical network. Okay, and then there's this input filter layer that multiplies each of the input variables by some coefficient beta. So then if we had this lasso penalty here on beta, these orange edges, if we set any of these edges to 0, then the network will not depend on that variable. So we could have done this with that group lasso penalty that we previously showed, but what we found is that if we only want to have 2 penalty parameters, this approach seems to be more effective. So, right, if you set some of these weights to 0, then you have removed these inputs. Okay, so by varying lambda1, which is controlling the input sparsity, and lambda2, that's controlling the network size or the network compactness, we can recover a variety of network structures, right? So if lambda1 and lambda2 were super high, we would end up just fitting a sparse linear model. But if, say, lambda1 was high, but lambda2 was small, we might be fitting a 5-layer sparse input neural network. Okay, so I spent a while on architecture kind of tuning or pruning. Now, one question that is kind of natural to ask is, well, if you're doing variable selection, are we actually selecting the right variables? And you all probably know that variable selection guarantees is generally kind of difficult to establish, even in simple settings like linear regression, or I guess for lasso, the linear setting with the lasso penalty. And it typically requires pretty strong assumptions. So once we talk about neural networks, the game becomes much harder, especially because this objective function is non-convex. So as a first attempt, we had looked into this issue. We found that under certain conditions, pretty strong conditions, we could establish that the total weight assigned to the irrelevant input nodes by sparse input neural networks would scale at a rate of square root log p. So that's kind of nice. We know that it's growing slowly with respect to p. So presumably these neural networks would be able to pick up on the right, or lasso penalized neural networks would be able to pick up on which variables are relevant, but the conditions are pretty strong. So rather than focusing on variable selection, can we say something about variable screening, which typically requires less stringent conditions? Okay, so what I'm going to do is give a kind of a intuitive explanation for how variable screening might perform in a neural network. So if we had a true model, F star, with its true support, S star, so that's denoted with this black box here, and S hat was the support estimated by our CRNet, the hierarchical version, we would see that, well, okay, S hat were these two nodes here, which means that we missed out on these two. So these are false negatives. And our question is, what is the probability of having a large number of false negatives? And what we found is that this is intimately related to this probability of having a large number of false negatives is intimately related to the predictive value of variables inside S star relative to the predictive value of variables outside of S star, which we kind of define as this gamma quantity. So like if the true support S star explained 95% of the variance, whereas this candidate support X1 and X2 explained 92% of the variance, well, we would see why the neural network got confused because the prediction accuracy doesn't really change too much if you got the true support instead. And so that's kind of, so that's why we have this quantity like gamma explaining kind of what this difference is. So if you have a sparse input, so we developed like these theoretical bounds for the probability of having a large number of false negatives. And the upper bound says, okay, this probability is small if the number of observations is at least 1 over gamma squared. So this means if these neural networks can perform support screening effectively, but we would need gamma to be large, which basically means our covariates have to be independent. And then there's also a lower bound that says any estimation procedure requires at least the number of observations to be larger than kind of this rate of 1 over gamma. And so this is somewhat more disappointing news, which says, well, you can't possibly get accurate support screening if your covariates are highly correlated. Right, so then this gives us there's kind of a dilemma here, like, well, we can't really trust the variables being selected then, because in a lot of cases, our data sets do have correlated variables. But one idea we might employ that could help us a bit is ensembling. So I'm sure you all have heard of ensembling, where you take a lot of models trained on the same data set, maybe bootstrap versions of the data set, and then kind of average together. And this is really helpful for models with high variance and low bias, like decision trees and neural networks, because we're just kind of reducing the amount of noise. And it has gained a lot of popularity, particularly in the neural network space as well, because it's thought to help us better quantify the uncertainty. And in some sense, ensembling can be viewed as an approximation of Bayesian model averaging. It's kind of a hand-wavy argument, but basically ensembling can be thought of as like randomly sampling map estimates. And this gives us some sort of estimate of the posterior distribution. So if we kind of view it from this Bayesian lens, maybe ensembling can help us. Rather than fitting a single seer net, maybe we can fit an ensemble, which I'm calling ensemble by averaging sparse input hierarchical networks, or easier net. And hopefully this ensembling will help us quantify the uncertainty of the true support. And then there's this other nice thing where ensembling seems to introduce some sort of grouping effect, right? So like if you have strongly correlated variables, different members of the ensemble will probably pick up on different subsets of this group. And if you average it all over, then we have some sort of grouping effect. And it's kind of like the analogy between lasso and elastic net. Here we have seer net and easier net, where easier net and elastic net are the ones kind of trying to group together these correlated variables and including that into the model. And here's just a simulation showing that it does, this ensembling does seem to help. Here we have a model that depends on 4 variables, x1 through x4. We've also introduced 4 irrelevant variables, 5 through 8. And we have x1 correlated to x5, x2 correlated with x6, and so on. And we vary that correlation from 0 to 1, so independent to collinear. And you can see, and these probabilities here are how often those variables got included in the ensemble. And we see that, well, when things are not correlated at all, we do pick up on the correct support. As we increase that correlation, we include more and more of the irrelevant covariates. And in the most extreme case where everything is, well, these variables are identical, the model obviously couldn't tell. And so it's just kind of a 50-50 chance. But that's kind of helping, that's an accurate kind of reflection of the kind of uncertainty that the model has about which variables were truly relevant. Okay, so let's actually try this out in real world data sets. So we have there's this data set with 46 gene expression there's a data repository with 46 gene expression data sets. They kind of range in their size, 10 to 50,000 genes, observations 10 to 300, and a lot of 2 to 7 categories. Yeah, and then as I mentioned before, we'll initialize these models with 5 hidden layers and 100 hidden nodes per layer. And then if we compare these EaserNet or SeerNet to these other models that are also kind of off-the-shelf machine learning models, what we find is that we do get superior performance. And we also achieve the top accuracy more numbers of times. So out of the 46 variables, EaserNet got the top accuracy 36 out of 46. So that's good. So we're fitting neural networks with only 2 hyperparameters, so not that computationally expensive, and yet we're also getting that performance gain. And we can also look at like how deep are these neural networks being trained. Here on the x-axis, I'm showing the average number of layers being learned. On the y-axis, I'm showing kind of the accuracy that the different models were able to achieve, or the maximum accuracy that models were able to achieve on the data set. And in general, you see that EaserNet is fitting a variety of data network structures. They do vary in the number of layers, and the number of layers tends to increase as the problem gets easier, as you can achieve more accuracy. And then we can also look at how many variables were selected, and comparing against logistic regression, EaserNet does seem to pick out select fewer variables into the model. Okay, so just kind of to wrap things up a bit, it seems like neural networks can be used for tabular high dimensional data sets, but it's not like you can just take an ordinary neural network and get it to work. You'll need some tricks like sparsity inducing penalties. And if you want to only tune 2 penalty parameters, you'll have to kind of carefully design the architecture as well as the objective function to kind of get that to work. And it seems like EaserNet kind of seems to work pretty well in that sense. And we have this ensembling piece, which helps us better quantify the uncertainty of the variable selection procedure. Okay, so here are some references. There's also Python and R code if you're interested. And thank you for listening. This is joint work with Noah Simon. And thanks, Jamie, for inviting me. Okay. Happy to take any questions now.
Thank you. That was an awesome talk. I feel like I learned so much and it was very interesting. So I would invite all of our attendees to please write in some questions in the chat, or if you want to ask them aloud, then press the raise hand feature and I can unmute you so you can ask your question. It looks like we have a couple of questions already, so I'll go ahead and ask the first one. Is from Akash, who wants to know, was the spin method compared to random forest methods that have variable selections like vsurf, which is variable selection under random forest?
No, it wasn't. Yeah, for that work, we mostly focused on the sparse additive models, but it could be worth exploring maybe in future work for sure.
Okay, our next question is by, cut off on my screen. Aniello wants to know, how does the EaserNet compare to logistic regression in terms of computational performance?
Yeah, so logistic regression is always faster, but it's not the neural network procedure isn't too bad either. So fitting a single neural network was really fast in these data sets that we were considering. It's like 1 to 2 minutes each. And then there are the 2 hyperparameters you need to consider, which if you parallelize correctly, won't take all that long either. So I don't know, it kind of depends on how you actually implement the whole thing, but it's not it's not like orders of magnitude off that it would be completely unfeasible.
Yeah, and it would probably depend on how big your data set is too, right? And how many predictors you're working with.
Yeah, I mean, the software for neural networks is pretty good. So like adding more variables and observations doesn't slow it down all that much. So that part I think is less of a concern. I think the bigger part is still the hyperparameter optimization, but because there's only two, it's much more manageable now.
Yeah. Okay, good. So Akash wrote back with some other questions. In the ensembling method, how does the simulation study show ensemble does better? And then there's a second question after that one. So you can go ahead with the first question.
Yeah, so it does a bit better. What I generally found is that ensembling helps boost performance a bit, because it does help you kind of quantify that uncertainty and might not select a bad model by chance. It's more helpful when you're thinking about like which variables are being selected. And you actually want to look at like if it was going to select those correctly. What did ensembling tell you about support uncertainty in the gene study? I don't think we actually looked at that. So, but that is an interesting question. These were the number of variables being selected by EasyNet though, versus logistic regression, where this is the log number of variables being selected. So I don't know. One thing we could learn is if you fit a nonlinear model, maybe you actually don't need that many genes to explain kind of what's going on. But we didn't actually look at the specific genes.
Great, those are some great questions. So, please continue to either write them in or raise your hand. So I had one other question. I think the variable selection part is really interesting, but then taking it to the next step, you often want to know, well, which variables are significant, or is there some way you can rank the relative importance of those variables? So I was curious if you had looked into that, or if you have any guidance for how you would do that in this framework.
Yeah, so I haven't actually combined variable importance with this, but I have done variable importance work. I've been writing papers on that with Brian Williamson, and also Marco Crone and Noah. So there's like a lot of different variable importance measures out there. Some of them, and it kind of depends what you're interested in, I guess. Like there are variable importance measures that basically say which variables does my current model think are important. And so for that, there's a lot of the current work in the machine learning literature, I think it's more focused on that. And you can use Shapley values and just kind of run it on your current network. Or you can take a derivative through your neural network and see kind of how much does my prediction change with respect to each of the variables. And then there are more population-based kind of population level variable importance, where we're not necessarily sure that the current fitted model is the actual population model, but hopefully it's close enough. And how do you quantify the uncertainty once you take all of that into account? So I've done more work in the latter. And the nice part about the population stuff is that, well, we can create confidence intervals and stuff for that, which is nice. The other thing is that assuming your estimation procedure converges at some fast enough rate, then basically you can plug in any machine learning algorithm to this second machine that calculates population level variable importance to get kind of these confidence intervals for variable importance. So like one measure is just how much does my prediction accuracy change when I remove one of the variables from the model. This this is kind of like ANOVA or like, more like ANOVA analysis, but kind of a non-parametric extension. But you can also do, so one issue with that is then when you have correlated variables, what do you do? So we have another paper that tried to essentially take into account or like average over all variable subsets. So like, what is the prediction accuracy when I train a model only on this subset of variables and I remove one of the variables, but then I average over all possible variable subsets to get kind of a general score for how important that variable is. I don't know, there's a lot of measures out there.
Yeah, that's really smart to average it over all the different subsets. I imagine that might be computationally expensive though.
Oh yeah, kind of the focus of that analysis, that paper we wrote was kind of the computation part.
Yeah, yeah, that's really interesting. So another question came in related to my question about variable importance, but it's, can we also get the sign of the direction of these variables that are selected within the method?
Yeah.
So I guess, you know, the direction of the association.
Yeah. That one's interesting. I think so. A lot of the ML literature for like Shapley values, whereas the variable importance for the specific model that you fit, they do think about this direction because when they define importance, it's how much does my prediction change relative to shifts in the variable. The population levels variable importance measures have primarily focused on how much does my prediction accuracy improve or get worse when I add or remove variables. So hopefully maybe there's a middle ground where you can do like population level association estimates, but I don't think I've seen anything so far on that.
So I have another kind of philosophical question. So I do some variable selection work also, but with random forests. And some machine learning people are adamant that you should not be doing variable selection because then you're losing information, you're losing that data that you need to make predictions. But like you, I also work in healthcare, and you know, it's just not reasonable to collect 1,000 things and then make a prediction sometimes. So I'm curious, you know, what your answer to that question is, because I'm sure you've had it come up too. You know, should you do variable selection, and what would you say to the critics of variable selection for neural networks?
Oh, I don't know. I feel like my reason is probably similar to yours, which is that you can't just throw variables at a model willy-nilly because some variables are completely useless, and your model will get confused. Just by chance, one of those extraneous variables might look correlated to the outcome, and it'll learn to depend on it, but obviously it's not going to generalize. So I don't know, variable selection does really help. Like you can see that, you can see it in the performance. Like a neural network that doesn't do any variable selection is really, really bad. At least for high dimensional data sets.
Yeah. So maybe this is also a naive thought, but because I don't really do neural network modeling very often, but is variable selection something that literally everyone is doing as a pre-step before modeling, or like how common is it?
I think so. Okay, so this is only for tabular data. I don't think variable selection is happening for, I don't know, image data or whatever. There, I think usually you think more about like attention, like where is the model paying attention to? Variable, I don't know, it kind of ranges. Variable selection is getting more interest in, there's been more interest in variable selection with neural networks. I've also seen just like practical papers and like, I don't know, just kind of a more biomedical journal where they're applying neural networks with variable selection. And usually then it's like a two-step process, right? Where you try to do some forward selection to figure out which variables to include, and then you fit your neural network after that. That seems pretty expensive.
Yeah. So another question came in from Akash. Can we still apply these neural methods to data that are not IID? Let's say you observe many folks over time, like hypoglycemia recording of individuals over time.
Yeah, I think you need to adjust for the correlation to get, certainly if you want to think about like uncertainty estimates. I don't know how many people have actually done that, but if you just want a prediction, these methods still will work. You might want to play around with the architecture, is that though, and the nice part is the whole thing is quite modular. Once we talk about kind of, I don't know, time series data or longitudinal data, you might want to consider different, I don't know, like people talk about like recurrent neural networks as well and stuff. So you might want to consider various architectures.
Yeah, and actually I can try to answer it too. So I do random forest for longitudinal data that are not IID. And in my work with that, kind of just keeping up with other methods being developed, I did find one neural network that's meant for clustered and longitudinal data. I don't know how well established it is, and I've never used it, but I do think, people are working in this area. And so it's another interesting problem. If you have additional information from a person over time, how can you incorporate that into your modeling?
Yeah, there's definitely a lot of work in the area. It just kind of depends on how deep you want to go, and what exactly you're going after. Are you going for like inference versus prediction? Like a lot of neural networks have been built for like the mimic data set with the ICU EHR data.
Mm-hmm.
All of that stuff is like longitudinal, clustered, has all those issues.
And also messy.
Messy, yes.
Yeah. Awesome. Okay, so here's another question from Peter. Are there some methods that group the unimportant variables together that would be taken out by lasso and try to gain some importance as a whole from these variables? I think it's some method similar to PCA, but my memory is hazy.
I don't actually know what you're talking about. That sounds interesting. Yeah, maybe that would work. I think it really just depends on how much data you have, right? Like you could have some unimportant variables and you would want to figure out how you can extract information from those variables. But you also need the data support to kind of like actually learn how you're going to combine those unimportant ones into something that's eventually important. Yeah, I don't know. I'll look up the method. I'm curious myself.
Yeah, I think it's always an interesting problem. If you're taking out more than one variable at a time, how do you do it? Because, different combinations might behave differently. So it's a very interesting and challenging computational problem.
Yeah, for sure.
Yeah. Well, we'll give it a few more seconds to see if any other questions come in. But Jean, this was an absolutely wonderful talk. Thank you so much for joining our group today. And I will just mention that our next webinar is September 28th with Byron Yeager, who will be talking about GitHub. So it'll be an introduction, and then also he'll get into some advanced topics with GitHub. So it'll be a really great webinar. So look out in your inbox for the registration for that, probably next week. I'll get that out. And seeing no other questions for Jean, I would just again like to thank you and thank everyone for attending the webinar today, and hopefully we'll see you next time.
Yes, thanks everyone.
Thanks, bye.